Now, I want to talk about something that bothers me. Not in the way that a hard problem in physics bothers me, which is a good kind of bothering, the kind that keeps you up at night with a pencil and a yellow pad. No, this bothers me the way a bad magic trick bothers me. The kind where the audience gasps and the performer smiles, and everyone in the room has agreed to stop thinking carefully. I am talking about flying saucers. I am talking about alien visitors. I am talking about the whole spectacular, glittering circus of the idea that some civilization from a distant star system loaded up a spacecraft, crossed the incomprehensible black void between worlds, and is now playing games with Navy pilots over the Pacific Ocean. I want to be very precise about something right at the start. The question of whether life exists somewhere else in the universe is a perfectly serious scientific question, and my honest answer is that it almost certainly does. The universe is enormous in a way that the word enormous does not begin to touch. There are roughly 2 trillion galaxies in the observable universe alone. Each galaxy contains hundreds of billions of stars. A significant fraction of those stars have planets. The chemistry of carbon and water and nitrogen is not some rare accident. It is the chemistry of the cosmos. The same atoms that built you are scattered across every corner of space. So yes, life probably arose somewhere else, very possibly in many places. That is a statement I am comfortable defending with numbers. But the moment you go from life probably exists out there to life is flying over our heads right now and choosing not to land, you have made a leap that the physics absolutely does not support. You have walked off a cliff. And I am going to explain to you precisely why, because the numbers are not ambiguous. They are brutal, they are cold, and they are final. Let me give you a picture to hold on to while we go through the physics. Imagine a desert, not a small desert, a desert precisely the size of the entire planet Earth. Now make it pitch black. No moon, no stars, no light of any kind. Now drop 2 people into this desert at random locations. These 2 people are completely blind. They cannot hear each other, they cannot call out. Each of them carries a single flashlight, and that flashlight flashes for exactly 1/10 of a second, once every 10,000 years. What is the probability that these 2 people ever find each other, or that one of them ever sees the momentary blink of the other person's light across thousands of miles of darkness during their brief 80-year lifetimes? The probability is not small, it is not negligible. It is indistinguishable from zero in any practical mathematical sense. That picture, that silent, black, impossible desert, is not a metaphor I made up to sound poetic. It is what the actual physics of the cosmos looks like when you do the arithmetic honestly. 2 civilizations in a galaxy of 400 billion stars, separated by tens of thousands of light years, each existing for a few thousand years of technological activity in a universe 13.8 billion years old, and you expect them to meet. You expect one of them to show up at the doorstep of the other. That is the claim we are examining. Let us look at it carefully. The first and most fundamental problem is speed. Everything in physics, and I mean everything, operates under a ceiling. The speed of light in a vacuum is approximately 299,792,458 meters per second. That is fast. I understand it sounds fast. But the nearest star to our own sun is Proxima Centauri, sitting at approximately 4.2 light-years away. A light-year is the distance light covers in an entire year of continuous travel. 4.2 of those. Our fastest spacecraft, Voyager 1, moves at roughly 17 kilometers per second. At that speed, it would take approximately 73,000 years to reach Proxima Centauri, not a neighboring galaxy, not the center of the Milky Way, the nearest single star, 73,000 years. Now, you might say, all right, suppose they are more advanced and they can push a spacecraft to a meaningful fraction of the speed of light. Suppose they manage 10% of light speed, which would itself require energy outputs that dwarf anything humanity has ever produced or conceived. At 10% light speed, you reach Proxima Centauri in about 42 years. That is manageable for a long-duration mission, but the galaxy is 100,000 light-years across. The distances between civilizations, if they exist, are likely measured in thousands of light-years, not 4. At 10% light speed, a trip of 5,000 light-years takes 50,000 years. But let us push harder. Let us say they get to 90% of light speed. Here is where the physics becomes an iron wall. As any object with mass accelerates toward the speed of light, its relativistic mass increases. The relationship is not linear. It follows the Lorentz factor. At 90% of light speed, the Lorentz factor is approximately 2.3, meaning the effective inertial mass of the spacecraft has more than doubled. At 99%, the factor is approximately 7. At 99.9%, it is approximately 22. The energy required to continue accelerating scales with this factor. To push a spacecraft of any meaningful mass to speeds approaching light speed requires energy that rapidly approaches infinity. Not large, not impractical, infinity. A spacecraft with the mass of a school bus, accelerated to 99% of light speed, would require the equivalent energy output of the sun running for thousands of years. No fuel source, no reactor. No engineering solution in any conceivable physical framework eliminates this requirement. It is not a technology problem. It is a law of the universe. The universe has set an absolute speed limit and has made the penalty for approaching that limit an infinite energy debt. But even if you could somehow achieve a significant fraction of light speed, the universe has prepared a second problem for you, and this one is less discussed but equally devastating. Space is not empty. I know it looks empty. I know the photographs of deep space show vast black voids between the pinpoints of stars. But space contains hydrogen atoms, dust grains, ionized particles, photons, and various forms of interstellar medium spread at very low but non-zero densities throughout every path a spacecraft would have to travel. At low speeds, these particles are irrelevant. A hydrogen atom floating in your path is nothing at walking speed, but at relativistic velocities, the physics transforms completely. When a single hydrogen atom impacts a spacecraft moving at 90% of light speed, the kinetic energy of that collision is enormous. The atom, from the perspective of the spacecraft, is approaching at 90% of the speed of light. The kinetic energy of a particle is proportional to 1/2 its mass times its velocity squared. But at relativistic speeds, the correction factors make it substantially worse. A single proton impact at those speeds carries energy comparable to a rifle bullet. Now consider that even the relatively thin interstellar medium contains roughly 1 hydrogen atom per cubic centimeter. A spacecraft, with a cross-sectional area of 1 square meter, traveling across 1,000 light-years, would encounter an absolutely astronomical number of such particles. The cumulative erosion, the pitting, the sputtering of hull material, the penetration of high-energy particles into sensitive systems, the radiation dose accumulated by any crew would be catastrophic. No known material survives this. No shielding of practical mass could stop it. You would need to carry so much shielding that your effective mass, and therefore your energy requirement, climbs back toward impossibility. The interstellar medium is not a gentle sea. At relativistic velocities, it is a continuous, high-energy particle accelerator aimed at your nose. The third problem is time. Not travel time, though that is also fatal, but the deep problem of cosmic temporal asynchrony. The universe is 13.8 billion years old. Our sun is about 4.6 billion years old. Technological civilization on Earth is perhaps 10,000 years old, and our ability to send detectable signals into space or to launch space missions is perhaps 60 years old. 60 years out of 13.8 billion. That is a ratio so small it barely registers in any meaningful calculation. Now suppose another technological civilization arose somewhere in the galaxy. What are the chances they arose at a moment in cosmic time that overlaps with our own technical window of visibility? What are the chances they developed their technology during a period when we were also capable of detecting them, or they of detecting us? The temporal window is extraordinarily narrow on both ends. And suppose they exist and they are advanced. A civilization capable of crossing stellar distances would require a technology base perhaps millions of years ahead of our own. A civilization, millions of years old, and capable of interstellar travel, would have access to energy sources and information that make our entire planet essentially invisible in the noise of the galaxy. The idea that such a civilization would allocate their resources to traveling thousands of light years to visit a small rocky planet around an unremarkable yellow star, and then, upon arrival, choose to fly around at low altitude so that individual humans with cameras can photograph them and argue about them on the internet. This does not hold together. It is not a scientific hypothesis. It is a story we tell because the alternative, that we are genuinely, perhaps permanently isolated in a vast and indifferent cosmos, is harder to sit with. And I think that is the real reason people want to believe in visitors. Not because the evidence supports it. The evidence does not support it. Every claimed sighting, every blurry photograph, every account of strange lights in the sky has alternative explanations that do not require abandoning the laws of physics. Atmospheric phenomena, classified military aircraft, optical illusions, sensor artifacts, misidentified planets and weather balloons. These are not exciting explanations. They are mundane. But physics is not obligated to be exciting in the way a movie is exciting. Physics is obligated to be true. What is genuinely exciting, what I find genuinely thrilling when I sit down and think about it carefully, is the real picture. The picture of a cosmos so enormous that the distances between possible civilizations render contact essentially impossible, not because civilizations are rare, but because the geometry of space and the brevity of any technological window make the universe a collection of isolated islands, separated by uncrossable oceans of time and distance. That is not a depressing thought to me. That is a profound one. It means that what we are doing here, the science, the mathematics, the careful weighing of evidence, the insistence on checking the numbers twice before reaching a conclusion, is not a small thing. It is the most extraordinary thing a collection of atoms has ever done in this corner of the cosmos, as far as we can tell. The discipline of demanding that something be demonstrated before it is believed, the willingness to sit with the discomfort of not knowing and keep working anyway, that is the most powerful tool our species has ever developed. It is more powerful than any comfortable myth. And the universe, cold and vast and indifferent as it is, rewards that honesty with something far more beautiful than any flying saucer. It rewards you with the actual truth of how things are. And in my experience, the actual truth of how things are is always more astonishing than anything we could have invented.